Welcome to Science and Engineering World, where we use the principles of mathematics and science to think engineering, act engineering, and practice engineering. In this presentation, we want to use a practical scenario to demonstrate some effects of fluid pressure. My name is Olutola Fakehinde. Surfaces are horizontal, vertical, inclined, and even curved. And fluid always has significant effects when it is in contact with any of the surfaces. We want to examine fluid pressure force on vertical and horizontal surfaces in this presentation. In a serious accident like this, can the driver in this car escape on his own effort? Let's examine this. The scenario here is that a car with a mass of 2,200 kg runs off the road in an accident and lands at the bottom of a lake 6 meters deep. The dimensions of driver's door are 1.2 meter long and 1.1 meter wide. Some 4 pertinent questions come to mind. Number 1 question is that, can the driver with an approximate effort of 1 kilonewton escape at the bottom of the lake? Number 2, if not, can he escape when the top of the door levels with the surface of the water? Number 3, if not, at what point can he possibly escape with his own effort alone? And number 4 is, what is the maximum energy that can bring the car up from the bottom of the lake? In solving this problem without much complications, we need to take some assumptions. The first assumption centers around the driver's door because it's a key factor in this problem. So the first assumption is the driver's door is rectangle with dimensions 1.2 meter by 1.1 meter. The second assumption is also about the driver's door. So we take assumption here that the driver's door is flat, that is, no curve on it at all. The third assumption is that the car is sealed, that is, water does not flow into the car. And the fourth assumption is that the water density of the lake is approximately 1020 kg per meter cube. And lastly, the fifth assumption is that the width of the car is 1.85 meters. Before we go into the solution of the problem, I want to encourage you to encourage us by subscribing to this channel. It is very important for us because YouTube uses some algorithms which includes the subscription, the liking of the video, the sharing of the video, and commenting in the comment section of the video. And we appreciate you for doing all of this. For those who have subscribed already, thank you. For those who are yet to subscribe, there is a red button at the bottom right corner of your screen. Please press it. press it now before we proceed to solving the problem. And at the same time, there is a bell. Press that for notification so that you can see as we drop videos from time to time. Thank you for doing this. Now, let us come to the problem. The car is there at the bottom of the lake, and like we've said, the key factor in the car right now is the driver's door, and we have taken an assumption at the top that the door is rectangle. Now, with the door as rectangle there, we will not be able to appreciate the forces acting on the door, but we can take a section view of the car from the behind the driver, and then we look from the front of the car so that we can see the driver and the water outside. That is the inside of the car, and then we can now see the driver trying to apply his own efforts on the car. The question now is, question 1, can the driver with an approximate effort of 1 kilonewton escape from this car? Now, as we have seen, the driver in the car is trying to apply a force on the car, and the water is also applying a force on the door. So there is an important point here which we need to find, and that is the point where the water is applying its own force. That's the total force of the water where it is applied on the car, and the driver should also be able to apply his own effort on that point. If not, he may not be able to open the car. But even then, let's see how far he can go with that. And this red point here is called the center of pressure. That's the point where it is assumed that the total force from the water is applied. There are a few things we must know here, and the first one is the center of gravity. The center of gravity, which is the point that is in red here on the illustration, this point depends on how much of the surface is wet by the liquid. Now, we understand this as we go on. However, for now, we know that the entire surface of the door is wet by the liquid. And so, we are going to say that the center of gravity is at that point there. Okay. Now, how far is the center of gravity to the level of the water? Is called H bar. That's the level of the water to the center of gravity. And this H bar is also very important. Now, we will see from here that the center of gravity of the door will be half of 1.2 because the entire length of the door is 1.2. So we will see the center of gravity is 0.6. All dimensions on this are meters. So we now have H bar, which is going to be equal to, so H bar will be equal to 5.2, which is from the liquid to the top of the door, 5.2 plus 0.6. So H bar equals to 5.8 meters. H bar is 5.8 meters. The next one we want to also point out here is the area of the door. Again, like we've said, this also depends on the area of the door that is wet by the liquid. Now, this door is completely in the water, and so the area A we'll be looking at is this 1.1 for the base and then 1.2 for the length. So the area here will give us 1.1 times 1.2, and that means area A is equal to 1.32 meter squared. So that's the area of the surface that is wet on the door. Another important point is the green point here, which I've mentioned above, is where the entire fluid appears to be acting. That is, the force that is applied by the fluid appears to be acting along this center here, which we call the center of pressure. And the center of pressure, HCP, has a formula that we are going to use. So HCP is equal to H bar plus Ig over H bar. So we have seen H bar, we have seen A. So what is Ig? Ig is the second moment of area of the door about the center of gravity. So we're saying that this is the center of gravity of the door, and so if the force Ft is acting on the center of pressure, we see that this will rotate in this form. That's the door will be in that form. Ig depends on the configuration of the surface. Now, if the configuration is rectangle, as we have assumed, it therefore means that Ig here, Ig is equal to BD cubed over 12. So what is B, what is T here? Like I said, if the force is applied at any point on the area, like say here, we see that this will turn around this point. So the D will be, because we are looking at that length here, the D will be this area, will be D, that length will be D, and this will be B. So in this case, we are now saying that Ig equals to 1.1 times 1.2 cubed over 12, and Ig is equal to 0.1584. And the unit is, because this is meter cube times meter, the unit is meter to power 4. Looking at the formula for HCP, which is the center of pressure, we have H bar, we have A, and we have IG. So all we need to do is now plug in these figures into the formula. So we now say that HCP is equal to H bar is 5.8 plus IG is 0.1584, 0.1584, and A is 1.32 times H bar is 5.8. HCP will now be equal to 5.8 plus all of this is 0.02 0.08 or 07 to take it to 4 decimal places, and adding it up, we now have HCP is equal to 5.821. You can break it to that 3 decimal places. So this is the unit here. We give us the unit of this. The unit of this is going to be meter 4, and this one is A is meter squared, H bar is meter, that's over meter cube. So meter 4 over meter cube will give us meter, and therefore this unit of H bar is in meters. So HCP is 5.821 meters. Now if you observe from here, we see that the center of gravity is 5.8 and the center of pressure is 5.821. Usually the center of pressure is always below the center of gravity. Now we need to calculate the force, because from here we know the driver has to be able to apply his own pressure, his own force on the center of pressure on the opposite side to be able to balance the forces coming from the fluid. What is the total force of the liquid on the door? Let's find out. The lake water pressure that is acting on the door can be obtained from P equals to gamma H bar. In the video that we've done above, I put a link here. We find that gamma is specific weight of the liquid, which is given as rho g. So we have rho to be equal to 1020 kilogram per meter cube times density times g, which is 9.81, and this gives us 10,006.2. The unit is Newton per meter cube. Okay, that is the specific weight of the lake water. Now we have area, and we know the area of the door, area A, is equal to 1.32 meter squared, and H bar we have to be equal to 5.8 meters. We have pressure and we have area, and we know that pressure equals to force over area. So we can now say that the force FTW that is acting on the door from here, F equals to pressure times area. So we can say the force Ft water F, that's the total force due to the pressure of the liquid, is equal to gamma H, which is the pressure, times the area A. Now we have the value of gamma, we have the value of gamma, we have the area, and we have the H bar. So we can now put all of these values into that expression, and we obtain a value for the total force that is acting on the door. Ft water is equal to the gamma we know, which is 10,006, as 10,006.2 times H bar, which is 5.7.8, times area, which is 1.32, and this gives us 607.4672. And what is the unit? The unit here is going to be for gamma, we know it's Newton per meter cubed, Newton per meter cube, and for H bar is meter, and for area is meter squared. So meter times meter squared is meter cube, and that will take this away. This is going to give us equal to 76,607.5 Newton. And this can be put in a scientific notation and say that FTW is approximately equal to 77 kilonewton. So this is how much water, this is how much force, the water is going to impart on the door. So we now have here on this side 77,000, that's 77 kilonewton, and the driver effort is 1 kilonewton. Now there is no way the driver will be able to escape at this point, because his effort is much less than the effort that is coming from the water pressing on the door. This is to conclude that the effort of the driver is very insignificant to the amount of force that is applied by the lake on the door. Therefore, he cannot escape at the bottom of the lake unless there is an external force that will assist him to come out. Well, it is obvious that the driver needs someone to rescue him from the car at this point. In part 2, we shall examine the possibility of him escaping when the top of the door is at the level of the water. I will put the link to part 2 at the top here and in the description section below so that we can examine this together again. If you enjoy what we have done and you find this video very useful, please do 4 things for me. Number 1, give us a thumb up. Number 2, share with others to enjoy the same thing we are enjoying. Number 4, we want to try to get your feedback. Give us your feedback. If you have any questions or concerns, put it in the comment section below and we will get back to you as soon as possible. And number 4, very important to us, and it is a way for you to encourage us, subscribe. If you have not subscribed to this channel, there is a button here, red button just below here. I want you to press that button now so that we will be able to move further to other parts of the world, and it will help this channel. Meanwhile, I always ask you, think engineering, act engineering, practice engineering. Until we meet in part 2, keep studying.